Hello and welcome to the Daily Space for today, January 10th, 2019. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Now, it is one of those weeks where we have science kind of coming at us from all directions. We have the American Astronomical Society meeting taking place out in Seattle, Washington. We have scientists around the world continuing their everyday science things. And we have periodic really bad news coming to us because of the government shutdown. Now, I don't have images for all of these things, so I bring you a picture of an eclipsing moon. This eclipsing moon is actually here as a reminder that not this weekend, but next weekend, Sunday night, going into Monday, Martin Luther King weekend here in the United States, there is going to be a total lunar eclipse visible in the, I'm not going to say early evening hours, unless of course you're a night owl like me, but starting at about 9:40 Eastern, the moon is going to pass into the Earth's shadow. This happens on average once a year, so it's not a really rare event, but it's certainly one worth using as an excuse to go out and get some wintertime star partying in on, I don't know. It's cold, it's beautiful. Go out, check it out. And the cool thing about lunar eclipses is we never quite know what they're going to look like. At that moment, when the moon fully passes within the Earth's shadow, refracted light bent through the Earth's atmosphere shines off of the moon ever so very faintly. We can still see it, but it's something different as the contrast changes and you no longer have that stripe of fully illuminated moon that reflects the sunlight. That moon that is simply lit with refracted light, its color is a reflection of our atmosphere. When there has recently been massive forest fires, when there's recently been a massive volcanic eruption, we end up with a bloody red-colored moon. When things are clear, when the atmosphere is clean, we end up with just a dark gray kind of moon. So let's all tune in about 10 days to see just what our Earth atmosphere decides to reflect, or in this case, refract off the moon. Now, in other news, the Hubble Space Telescope's Wide Field Camera 3 continues to not be in use because the people who could fix it are furloughed. And in other news coming to us from the American Astronomical Society, there is a tweet from Deborah Good documenting that if the shutdown continues until late January, there will be no more National Radio Astronomy Observatory travel. In mid-February, telescopes start turning off. ALMA, VLBA, and GBO may have a little bit longer due to existing allocations of funding. It's unknown if the radio data archives will stay up at this point. So we're starting to see real problems hitting the astronomical community. NASA issued this morning a delay of when proposals will be due, and they didn't give a date. When you delay the due date of proposals, it also means that you're delaying when those proposals will be reviewed. You're delaying when the money will be issued. That means that you're essentially saying that for those few who do get the awards, you're going to have to find a way to just hold on a little bit longer without pay, as so many people are probably going to have to start holding on next week without pay. Now, since I am no longer funded by NASA, I can tell you, go out, call your Congress critter. Go out, call the White House switchboard. Tell people what it is that you want, whatever that may be. Make your voices heard. Now, we are here for the science, and there is still science that is finding a way to make itself done even in this crazy world that we live in. In this case, I have a story of a quasar. This is a distant galaxy containing a supermassive black hole in the process of eating material. That disk of material that is spiraling in towards the supermassive black hole, that is what gives off all the light that we see. When we talk about active black holes lighting up galaxies, it's not the black hole that lights up anything. It's not the black hole that has jets. It's that surrounding disk of material that's spiraling in towards the black hole that is responsible for all of these things that the black hole gets credit for. In this particular case, we have a distant galaxy, and in between it and us is a foreground system. And that foreground system is bending additional light from the quasar that otherwise would have flown off in some other direction of space. The mass from that intervening galaxy is bending that light, amplifying the number of photons that we're able to receive, making this both one of the oldest quasars in the sky that we see and one of the brightest. This is an object that we are going to follow up for years to come. Now, this is just a cool story, one of many, coming to us from the American Astronomical Society meeting. We are about to experience a really cool press conference if the press releases that I read this morning have anything to say about what is to come. Now, I do need to do a quick scene change, and once I have done that, I will answer all of your questions. So please type them into the chat, precede them with @CosmoQuestX to make it easier for me to find them. And as always, I just want to let you know, the Daily Space is part of CosmoQuest. We are here to put science in your brains, and we are a production of the Planetary Science Institute working in collaboration with Youngstown State University. Now, please hold on just a moment while I switch things over so that we can begin to see the press conference when it goes live. I have to just remember to click the correct series of windows in the correct order, so sorry. There we go. We are now ready so that when they go live in about 5 minutes, we will be able to bring you all that is new coming to us from the American Astronomical Society's 233rd meeting in Seattle, Washington. Now, to see what questions there are. So I see Ed Thompson is asking, the object bending light, is that an example of a gravitational lens? Yes, that is exactly what's going on. So to give you a twisted example as best I can, we have a small, faint, hard to see background object. This small, faint, hard to see background object is radiating light in all directions. And some sort of an intervening mass causes light that would normally shine from this background object off in a strange direction to instead get bent. So the light gets bent by that object. And this means that you have the light that would normally travel straight towards the observer, as well as light that would normally have gone in a different direction, all reaching us. Now, this does imply that for other directions, the light is going to be a little bit fainter. So we are kind of in just the right place for this kind of observation to be taking place. Thank you for noticing that the internet is working better. It is definitely working better, and we are very excited that the Twitch servers have granted us a bigger pipeline today. Now, I do have a background puppy that is destroying something. Please pardon me for one moment while I take the crinkling noise away. What do you have? You can't have that. We have a puppy. We have a puppy that likes to make loud noises. So do we have any other? So Mike Cassidy, you can't join any citizen science projects at the moment. We're hoping that we're just a few days away from being able to get all of those relaunched for you. We're doing massive upgrades to everything we do, and it just takes a little bit longer than we had thought to get that last 5% of the work done. But we will be getting it to you as quickly as we can. Oh, AutoMod. There we go. Yes, Stella needed to come up and say hello. Either that or she needed to eat the garbage. I preferred to pick her up. Okay, other questions out there in the audience? We are 2 minutes away. I'm going to see if I can get the chat open while we wait. Nope, it won't open. Okay. Okay, so now we wait. I have a squeaking dog now. So Ed Thompson is making a comment. Yes, credit unions are basically the not-for-profit version of a bank, is the way I think of it. So Life Taking Biatch is asking, can you recommend some good websites for keeping up with physics news and research? Phys.org, phys.org is always a good site. There is also lifesciences.com. Sorry, Live, L-I-V-E, science. They cover all the different sciences together. I have to admit that because I'm not focused strictly on physics, I can't recommend any strictly physics sites right off the top. So Bill Wink, I actually decided to pretty much boycott NIAC-NEAF because they have no featured female speakers for NEAF, and if you look through the archive of speakers that they choose to feature on their website, there's very, very few women, and they don't feature all the women who have been featured speakers at their conference before. So things like that are a bit disturbing. So Archive is a good site. It's just hard to weed through because some of the things on it are really good and some of them are just not. So let's see if I can get this to play. Now, let's reload the page. It's always a bit of a challenge to try and get this up and running. There we go. Okay, stand by. Live webcast will begin soon. Do you want down? Is that the issue? You don't know what you want. Here we go. Well, we had it for a moment, and then they changed their mind.
You seen it? Okay, great. Good morning, everyone. Welcome to the fourth and final day of science presentations at the 233rd meeting of the American Astronomical Society in Seattle, Washington. I'm Rick Feinberg, and I'm very pleased to see a nearly full room again for the first of two press conferences that we'll have today. This one, remarkably, is the fourth out of 8 that concerns exoplanets and their host stars. But that shouldn't surprise you too much, because if you looked at the scientific program, you'd see that it is heavily dominated by exoplanet papers. That field has certainly come into its own. We're going to have 4 presentations today. I'll introduce our 5 speakers in just a minute. But first, I want to remind everybody to please silence your cell phones or other electronic devices. I want to mention that we are webcasting, and my colleague, AAS Media Fellow Carrie Hensley, is monitoring the webcast. The way the briefings work is that I'll introduce everybody, and they'll speak in turn, and all the questions will be at the end. So please hold your questions till the end. There is at least one press release going out to the AAS press list in connection with this briefing, and there will be a whole bunch more later. Okay, so as I said, the session is about exoplanets and life beyond Earth. We have 4 presentations. The first is a tag team presentation by Thane Curry and Olivier Guillon from the National Astronomical Observatory in Japan and the Subaru telescope on Mauna Kea. It's characterization of extrasolar planets with the, how do you say it? How do you say the name of your instrument? Skexio, what he's just said. Cheris on Subaru. Then Thane and Olivier will be followed by Benjamin, is it Montet or Monte? Monte from the University of Chicago. A search for transiting planets in NGC 6791, which is a star cluster. Next will be multiple large impacts revealed by variability in the disk around a young star by Kate Sue from the University of Arizona. And then Ed Guinan from Villanova University, who may hold the record for the number of appearances in a press conference that I've hosted, will be speaking, Can Life Find a Way on Barnard's Star's Super Earth? With that, I'll turn it over to Thane and Olivier. I'm not sure which of the two you want to pull up first.
Good morning, everyone. So we're delighted to tell you about the Subaru chronographic extreme AO Skexio system, which is a system that is targeted at imaging and characterizing exoplanets and disks. So it's part of a very fairly large international effort which combines scientists and technologists. So on the first slide, you can see a list of the teams we are deeply involved with. And what we're doing is essentially 3 things. We are observing with the Subaru telescope nearby stars and imaging planets and disks around these stars. The planets we're imaging, as Thane will describe, are essentially giant planets, bigger than Earth. But at the same time, we are developing technologies and aggressively validating them and including them in the instrument. This is an ongoing process which includes several high technology groups, people who develop those technologies. And our long-term goal is not only to feed these technologies into Subaru telescope and current telescopes, but it's really to prepare, I think, what is our one of the biggest challenge and opportunity of the next couple of decades. It's enabling imaging habitable planets with the upcoming large telescopes, the 30-meter class telescopes. So at Subaru, we are under NAOJ, which is involved in the 30-meter telescope, TMT, one of the partners of the TMT. So we're specifically looking at deploying these technologies on TMT. But the big picture is we're developing technologies for all of the large telescopes so that we can image and characterize habitable planets with these large telescopes. So what is Skexio? How does it work? There are really 3 main functions. The first one is to do wavefront control, essentially removing the turbulence in the atmosphere, making the image very sharp so that we concentrate the light of the star in a single spot. And then the next step is a coronagraph. The coronagraph is an optical device to mask the light from the star, but at the same time we need to maintain to keep the light from the planet. And once we have done these two things, light goes into the instrument, essentially the camera, which takes the light from the planet, images it, and takes a spectra of the planet. And Thane will show you some examples. So some of our capabilities, they are illustrated here by images, on-sky images that we've been taking. The first thing at the top right, you can see an image of a star, Mira. It's a well-known star. It's not a star around which we're looking for exoplanets. It's a star around which we're looking for dust, which is another thing we do. But what's unique about this image is it's a visible light image. And adaptive optics, extreme adaptive optics, allows us essentially to remove the effect of the atmosphere and image the star as it really is, not as a point, as shown in a small inset. When we look at a reference star, we see a small diffraction spot with a ring. But when we look at a big star, we actually resolve it as a star with a big spot that you can see here in the star. But most of the science we do is in an infrared, in the near infrared. And what's unique about SCEXEO is the ability to maintain high level of wavefront correction on faint stars, such as the example here, which is a star which is called Lick Calcium 15, which is by astronomer standard in this field considered as pretty faint. And the other thing we do is very deep imaging, deep contrast imaging, so that we can look at planets such as the image on the lower right here, which is a well-known system with 4 planets. You can see 3 of them here. The 4th one is actually outside of the field of view of this image. We have, as I mentioned, we have a lot of exciting technology developments going on. Here I'm showing you one. We recently installed what is probably the most advanced camera technology in the near infrared. It's a photon counting camera. You can see individual photons hitting the array, and you can also measure their wavelength in real time. And that's critical for us because our next phase is to control what we call speckles. They are those leftover residual starlight that look like planets, fake planets, and we need to actually measure them, sense them, and cancel them very fast. So this camera is critical to our goals. And it was built by UC Santa Barbara. It uses very exotic technologies. It's inside this duo, the temperature is actually less than, it's about 100 millikelvin, so about 0.1 Kelvin. It's a very cold, quiet place to be very sensitive. So I'll hand over to Thane, who's going to show you some of the science results we've recently obtained.
So how do you get this back? Okay. And just let this load here for a second. Okay, so thank you, Olivier. So I wanted to follow on Olivier's discussion and talk about some specific science results we've been able to attain with SCEXEO. And to get right down to it, SCEXEO now is in its first full year of science operation with our integral field spectrograph, and it is already presenting a clear new advance in our ability to image planets around other stars. And so to kind of illustrate what we've been able to do in the last 20 years and how SCEXEO is the next evolution in our capability, I've shown images for one system. This is HR8799, the multi-planet system. And as you can see, with conventional AO facilities that you would normally get pre-packaged with a system like, or a facility like Keck or with Subaru, we can barely see a few of these planets or maybe even just a subset of them. With extreme adaptive optics, such as been pioneered with the Gemini Planet Imager or with Sphere, we can see all 4 relatively easily. And now with SCEXEO, we can obtain these images even more cleanly. So this is great. So what have we been able to discover so far? Well, we've been able to focus mostly on characterizing known planets and be able to understand their spectra in much more detail. And these are exciting objects. So for example, as some of you know, the public loves exoplanets. Sometimes you have a planet that has a band named after it or a song named after it. I think Kappa Andromeda b, which was discovered with Subaru a few years ago, is the only planet with a beer named after it. And so this was a lot of fun to be able to see this develop and see the public gain interest. But this object was also controversial, and that's because in order to properly interpret this object, we need to know the age of the star. all these planets we've been able to image are gas giants, and our inference about the mass of these planets critically depends upon the age of the star. So you had two competing papers that preceded ours that came to different conclusions on how old the star was, and thus by inference how massive the companion was. And so what we needed to do is look at Kappa and B in more detail to get a really good crisp spectrum of this object to kind of see whether it looks more like a planet or a low-mass brown dwarf. And so this is our image, and we have this very high signal-to-noise detection of Kappa Andromeda B. We can actually see the planet in the raw data without any PS subtraction techniques applied. And the really key thing with this object is it appears to have a very sharply peaked spectrum at H-band, and that's at about 1.6 microns on the plot, as you can see here. We've been able to take data for this over a couple of years, and it appears to be eccentric on a wide orbit separation and maybe aligned with the rotation axis of the star, which is what you would expect for an object formed in a disk around a young star. And if we compare its spectrum in detail to a suite of other objects that cover a range of ages and a range of masses, this looks like a young planet mass object, albeit one that's at very wide separation and probably formed a little bit differently than Jupiter formed in our own solar system. And that's just one of the many science papers that we have come out recently. Skexio covers a wide range of science interests, from studying binary stars, Kuiper-Belt-like debris disks, looking at the statistics of high contrast imaging. We've had several presentations on this during the conference, including one case from Evan Rich where we've actually refuted a planet. We also have a paper in preparation that looks like it might be refuting 2 or 3 more, but we are also trying to discover new planets. So our sort of long-term goal with Skexio, as Olivier said, is to sort of set the baseline to be able to image Earth-like planets around nearby star with extremely large telescopes. In the near term, what we're wanting to do when we get to a point where we're happy with the performance of Skexio is to be able to combine it with a precision radial velocity instrument, which is able to infer the presence of planets indirectly through the stars spectrum, and have a dedicated survey, an intensive
They seem to be having internet issues on their end today. As soon as their feed returns, we will be happy to share it with you. For now, do you have any questions? Oh, here we go. Let's see.
And even though it ended 6...
Too soon. Okay, so I don't know what to say other than the internet
years
is a
ago,
hateful thing.
there's still tremendous science coming from this mission. The Kepler Guest Observer Office keeps detailed track of publications using data from Kepler and K2. And here's the end of Kepler, and you can see that every year since Kepler ended, more papers have been written using data from this mission than any year when it was actually operating. So you might be wondering by now, we've had 4 years of Kepler plus 6 years post-Kepler. Have we found all the planets? Isn't Kepler done finding everything? And the short answer is no, and the longer answer is no, and I'll tell you more right now. So Kepler, during its standard planet-finding mission, worked by drawing small apertures on the detector, small regions of pixels that were attributed to a specific star, and count how many photons hit the detector in that aperture and say, this is what we're going to use to find the planets. That works great when stars are widely separated and you can assign specific pixels to specific stars. This is a fairly random section of the Kepler fields, what most of it looks like. Sometimes it looks like this when you have a star cluster, which is a cluster of stars all together that are coeval formed in the same group. And so when you have this, it's much harder to attribute specific pixels to specific stars. They all overlap. It's hard to separate these out, and other specific stars dilute other stars, making it harder to find planets. To orient you on the Kepler fields, this is the original Kepler field. This is the first light image from Kepler, and this is the cluster we're looking at way in the corner. Planets and clusters are important because they tell us something about the timescales of planets' formation and evolution. It's really hard to measure the ages of stars, but it's easier to measure the ages of clusters when you have thousands and thousands of stars to use to understand. And so planets and clusters are planets with known ages. There's been a lot of beautiful work from the K2 mission looking at very young clusters to understand the timescales for planet formation. NGC 6791 is a very old cluster, which allows us to understand the timescales for planet destruction. It's old. It's about 8 billion years old. It's metal rich. The stars in this cluster have about twice the metal content of the sun, which puts it in a unique place and allows us to understand planet evolution in a place where we don't really have a lot of data right now. And this is enabled by Kepler, but it's also enabled by Gaia. The two instruments working together on this cluster provide a lot of detailed information that neither could alone. Okay, so how do we do this? How do we find these planets? Well, we know from Gaia very precisely where all of the stars are in this cluster, in this field towards the cluster. And from Kepler, we know what we call the pixel response function looks like. So given a photon hitting the detector, team made these images available. So we know exactly if we know the positions of the stars, what they're going to look like on the detector. And so we can model, rather than just summing up specific pixels for each star, we can model this behavior on the detector for all 7,000 stars in the field of view of this cluster, build light curves, and search these for planets. This is an example of a light curve. You can see many of the systematics that are inherent in original Kepler data still here, but you can see deep dips, 6 of them in this caused by, in this case, a binary star. So what do we find? We find new planet candidates. Here are some of them. This is another place where Gaia is very important because Gaia tells us how these stars are moving on the sky. So we can learn which stars are actually moving with the cluster and which just happen to be chance alignments in the sky near the cluster, but at a much nearer to us or much further away. In these cases, they're almost always much nearer to us. So some of these we can say are just chance alignments. Others are actually in the cluster. One thing that's really interesting here is that there are no very short period planets. You would expect a few so-called hot Jupiters, especially because this is a very metal-rich cluster. We don't see any, and that's a little weird. However, we know that hot Jupiters are destroyed through tidal inspiral. The star and the planet raise tides in each other, which cause the planet to spiral into its host star. We've seen evidence for this in the WASP-12 system. There was a paper a few years ago that predicted that perhaps for a cluster of NGC 6791's age, about 3/4 of all hot Jupiters would be destroyed. And the 0 hot Jupiters we see is consistent with that. So it seems to be predicting, these predictions of tidal destruction of planets seem to match up pretty well with what we see. We also find some new eclipsing binaries. This one I really particularly enjoy. You can see 6 eclipses right here. This deep one is when the cooler star, the cooler, smaller star passes in front of the hotter, brighter star. And this is when the opposite happens, when the cooler star passes.
AAS is having a lot of internet difficulties today. I apologize for the constant breaks. I'm not quite sure what is going on. This is occurring on their end of the stream and not on our end of the stream. We will be back as soon as they are back. For now, please feel free to go ahead and ask us any questions you may have. Yes, in spiral essentially means that you have an object in a disk of material, and as it consumes the material further in from the star than it gets frictionally slowed down, and that drags it in towards the center of the system. And because it might work, I'm just going to reload that page, see what happens. Now, There's no reason to think that that would do
A
anything.
graduate student I'm working with who happens to be standing in the back, Adina Feinstein, is working on. You heard about her on Monday, talk about some other science. So these are the main takeaways that I'm really excited about. We're using new techniques to find planets still hiding in the Kepler data. These are not the last planets that will be found in Kepler, I'm sure. We're doing this because Gaia and Kepler together make a great team. And these planets are enabling us to understand the long-term evolution of planetary systems, which is something that will continue with tests. So thank you.
What do I do? There. See your presentation. There. Is it there? Okay. Thanks for coming. So this presentation is about terrestrial planet. Okay. So terrestrial planet and computer model tell us that rocky planet grows by pairwise accretion from smaller body planetesimal through long-array growth into planetary embryo, bigger body like big asteroid, and followed by a final phase of giant impact, such as this simulation shown here, if I can clip it. Yes. So this giant impact process is actually quite inefficient in a way that is only 50% this giant impact, big body collide together, will lead to a net growth. So to form a terrestrial planet like Earth, you probably need roughly a few dozen of these big collision, big bodies smashed together to form an Earth-like planet. So this inefficient process is actually why we see a diversity of the composition in terrestrial planet in our solar system. We know that Mercury has a big core, and with a very thin mantle. But our moon is mostly mantle material. This is exactly because there's a wide diversity of the collisional result due to a giant impact. And computer model also tell us that each time there's a giant impact happen, it will produce a lot of dust and dump into the system. And this dust can be measured by infrared flux. So on the graphic I'm showing here, the color lines are the numerical simulation for rocky planet formation for 3 different realms. So every time there's a giant impact happen, it creates a spike that you see on the plot and dump a lot of dust that we can measure in the infrared. So the $1 million question is that, can we really see a large impact happen in real time around young star? If so, what kind of signature? What should we look for? So that brings to the focus of this presentation a star we call IDA, somewhere here. It's a solar mass star in a cluster which we know age, NGC 2547 in the southern constellation Phala. It's pretty far, like many of the young stars. It's roughly 1,200 light years away. But because it's associated with a stellar cluster, we know it's very young. It's only 35 million years old. For a better analogy, if you think of Sun is a 40 years old adult, and IDA is actually only a 3 months baby. It's really, really young. And it's actually the time when our solar system is forming rocky planet. So the beautiful image here is the optical image of the cluster. And you probably can see at the center, that's IDA. It's nothing spectacular when you look at optical image. But when you look at infrared, it's very bright. It's much brighter relative to other members of this beautiful more massive member. It has a lot of dust around it. So we know it has a lot of dust around the system. It's very, very bright in the infrared. And one thing I want to draw your attention is about the orientation of the system. Because it's a very young star, it has a lot of stellar spot on the surface. By monitoring the optical light curve of the spot, we know the rotation period of the star very well. We know that the rotation axis of the star is roughly perpendicular to the line of sight. So if the system have a disk,
I apologize.
what do
for
we
the-
see? So using Spitzer back in 2014, the story is that we have monitoring the system at different times. So the plot show here is the infrared light curve taken at different time. So the Spitzer was monitoring the star and monitoring until the star go behind the sun. Spitzer cannot look at it, so we have a gap. Just by comparing the light curve before the star going to behind the sun and after it came out, we see a brightening event just by comparing these two light curves here. There's a brightening event, and you create a lot of dust. You see a lot of infrared flux go up. But limiting by so at that point, we know that it has to be a large impact happening, creating a lot of dust, producing a cometary like cloud, orbiting the star, creating this infrared signature. But limited by our modeling ability, we couldn't say much about the impact, where it happened, exactly when it happened. So that was the work that we published in Science back in 2014. We actually have a press release on that. So since then, we came out with some better model. Using our better model, including dynamical evolution, a collisional evolution that created within the debris of the cloud, we can actually see a cloud forming and how it orbits the star by modeling its evolution. That will create this up and down light curve. So we can use that better model to predict where it happened. So for this impact, it happened at 0.43 AU. And exactly should be on October 26, 2012. That's because we can pinpoint the location of the star, the period of the star. And by modeling the infrared decrease, we know that impact has to create a lot of vapor condensate, millimeter to centimeter size. And through this millimeter to centimeter condensate, it has to be created by a hypervelocity impact that vaporize part of the impactor and then condense quickly to a millimeter droplet. And that has to come from a hypervelocity impact involving a big body, a large asteroid, like more than 100 kilometer size. So great, we now have a better model. We can explain in the light curve. So since then, we've been using Spitzer, continue monitoring the system. So in the past 5 years, we had all the data from 2012 all the way to 2017. So what I showed earlier is only this first part, 2012 impact. Now let's focus on a later data around 2014 and 2015, we see another impact. So let's zoom in to that part. We see up and down due to an impact cloud forming orbiting the star. Using our better model, we can pinpoint that the impact has to happen in early 2014, and the location is about 0.24 AU from the star. It's also it's slightly closer than the previous impact. Just by modeling the infrared flux increase rather than fading, we know that the debris generated by this giant impact has to be like a border.
I'm sorry, the internet issues that we're dealing with currently appear to be on the end of the American Astronomical Society, and there's just nothing I can do to sort this out.
At 0.43 AU. And later on, in the early 2014, we have another big impact happening at 0.24 AU, slightly closer. And the rest of the either flux increase or decrease is consistent with the collisional evolution of this impact-produced cloud, and that I don't really have time to talk about. But the bottom line is that we see these two impacts happening at very close to the star. The first one is at 0.43 AU. The second one is about 0.24 AU. They're very close. Not only they are very close, the angle between where it impact relative to the end of the disk, this angle. The first one is 70 degrees. The second one is 90 degrees. So in my opinion, they probably are somehow related in a way that your first impact is some kind of hit and run or grazing impact. There's a big chunk that's created by that impact, escape, and somehow come back to hit to a similar time, similar location. This is kind of hit and run, multiple hit and run collision has been proposed to explain Mercury that's through many kinds of big giant impact. You basically destroy all the mantle, leave at a big core. So to summarize, I think computer model tell us that building terrestrial planet, a rocky planet, is a very massive process. And through Spix's dedicated monitoring on the IDA system, we finally can confirm this by tracking the evolution of the impact debris. And to me, I think that's very exciting. Thank you.
This is the talk I was waiting for. If he can sort.
What do I press that one?
Just give it a double click.
Double click. Okay. Well, thank you for coming. I'm going to be talking today about Barnard Star Planet. And our title is on there, X-ray UV optical irradiances of the star, of the planet, I mean. And it's a super Earth, and we're looking into the possibility that the planet could have life. My collaborator, Scott Engel, is over in the audience. Raise your hand. Wasn't enough room for him up here. And it's too far for my other collaborator to come. He's in Spain. Okay, what do I press? The up button? Huh? Up. Right up. Got it. Okay. The background for this is that we've been doing this for 20 years. And we call our program Living with a Red Dwarf. And it's sponsored by NSF and NASA and all that. And the major thing here is to try to characterize the star and then understand the radiation that the hosted planets are getting. This was our logo that was not condoned by NASA. So Barnard Star, let me go back to a short history of it. Barnard Star was discovered in the 1890s, but it was E.E. Barnard who discovered its large proper motion. Up to that point, Kapteyn Star had the largest proper motion. It was 10.5 arc seconds per year, and also it has a large, its distance is rather near, 6 light years. So after Alpha Centauri, it's the second nearest star system. It had some bad notoriety. It was the first star to be conjectured to have planets back in the 1960s and 70s. Peter van de Kamp did astrometry from 1938 on and discovered or published, thought there was 2 Jupiter-sized planets. 11 years and 27 years, and later on it could not be confirmed, and it turned out it was cleaning the lens of their telescope that produced a tiny change. And later observations with HST showed there's nothing of that size orbiting the star. The third point to its claim to stardom is most recently, 2 months ago, my colleagues did an analysis of radial velocity observations, 20 years of it, and teased out the discovery of a planet orbiting with an orbital period of 233 years, mass of 3.2 or bigger, and having a distance of 0.4. It's the same distance that Mercury is from the Sun. One of the interesting things here is its angular separation is 220 milliarc seconds, so it leads to possibilities that it could be imaged. This is the Nature papers. This is why this is a late paper, because we announced this 2 months ago. And that's the Nature paper that came out on Barnard Star. It's called a Candidate Super Earth orbiting near the snow line. It's cold. It's minus 170 degrees C, even because the star is dim. This is our study in our living with a red dwarf. We're knocking off all the stars within 10 light years of the sun. When we started this project, there were that star symbol, they're the ones that have been found to have planets.
Again, they're having internet issues out of the American Astronomical Society meeting. I'm not sure what's going on there. And the star that he's talking about, Barnard's star, is about 6 light years away from Earth. It's a high proper motion star. The planet,
rotation periods and all that, of most of the stars within 10 light years, and that just shows some of them. No, we started this program 20 years ago. We were waiting, for a planet to be discovered around Barnard's star and Proxima Centauri, and it happened. This is the properties. This is a scale drawing, kind of. It shows the planets, the sun and the inner planets of the solar system and the star, and it gives its properties. You can barely see them there. You see Barnard B. So it gives you the equilibrium temperature is rather cold. Now our results. So this is a major part of our program was determining the ultraviolet and X-ray exposures to planets hosted by M dwarfs. And I'm just going to give you an example. Barnard star, the top there, S over SE is the irradiance. The other two are how much X-rays the planet is getting relative to Earth and how much ultraviolet radiation the planet is getting relative to Earth. You see that Barnard star is only getting 2% of the radiation light that Earth gets. So that's why it's cold. But notice the X-rays and UV are about this, a little bit less than the Earth. Take a typical red dwarf planet in the habitable zone, which is like 0.05 to 1/10 in AU. Notice the amount of optical radiation is fairly high, 0.65%. So it's going to be warm or temperate. But notice the other two numbers. The X-ray radiation that planet, that Proxima b is getting is 600 times more than the sun, more than the Earth, and in ultraviolet 130 times. And that's when it's quiescent. When these stars flare, this can jump up by 10. So one of the problems with red dwarf stars in the habitable zone is that they are getting irradiated with strong X-ray and UV radiation that actually could blow away water, their atmospheres and things like that. On the other hand, you can avoid that high radiation levels if you don't mind the cold, as in the case of Barnard B. We get ages. We have developed over the years rotation age, X-ray, luminosity age relationships for stars. 20, 30 stars are in there. And we determine the age of Barnard star using a rotation. 145 days is about 8.5. Habitability. There's not a lot known about super Earths. So one of our problems is the models. They're all around the place. And so what I give you there is that it is 3.25 masses of the Earth, minimum mass, and it depends on how it's inclined. The top right panel shows the Earth and various terrestrial super Earths. And so that our guy is between 3 and 6. And you see that out where it lives, it's going to have, if it has water, it'll be ice. And down the bottom of that, we're discussing habitability. Super Earths could have large iron cores and still hot. And they may not be volcanic because of the larger gravity. They may not have eruptions on the surface, but there's radiation leaking out of there. The two models that we use are that's kind of in that one corner is Europa, which is heated by tidal interactions with the planet, or this would be geothermal. One of the things that can happen is that if it is bigger, if it gets up to be 7 or 8 times the mass of the Earth, it might become, the gravity is so strong that it retains its initial atmosphere of hydrogen and helium and becomes what's called a mini Neptune, and that would preclude life, because probably, unless it had a moon or something like that. An example of what we're looking at, we have a terrestrial example of what could be happening on this planet, and that would be the lakes, hundreds of liquid water under the ice caps of Antarctica. Lake Vostok is the big one. So that's water under there is because of geothermal heating. So these lakes, which are as big as the Great Lake, and are there because of that reason. And they're probing these lakes now to see if they have any life. There's some evidence of life in one of the lakes. So that's our analog, closest analog to what we are dealing with, is the geothermal heating of what we find in Antarctica. Imaging, yes, it is on the hairy edge of being imageable. The major thing is the third nearest, actually the second nearest star system. The planet itself, we computed what that would be. The H, if it were an Earth-sized planet, it would be 25. If it were a little bigger than that, it would be, this is magnitudes, the H would be 23, which are on the edge of being visible. Their ratio of planetary luminosity or light to the star is 10 to the minus 9th to 10 to the minus 8th, in the best case 10 to the minus 7th if it's really a bigger one. These are beyond the edge of what can presently be imaged. So I just determined, I looked into SPHERE, which is operating now on VLT, and I tried to get observing time, and I was, even though it's a kind of a risky proposal, I heard another group got observing time. So maybe they'll see something there. It's really on the limit of being observed with that. So the major thing here, it's one of the only Earth planets, nearby Earth planets, that can be imaged. Proxima is 40 milliarcseconds from its host. And even though it's nearer and it's in the travel zone and all that, it is not imageable in the near future. Not so easy to image. You have to go in space. And maybe first with a shroud or something could do it. So the imaging is very active here, very active pursuit. People are looking into it. JWST, it's on the edge of, it has to be a kind of a mini Neptune to be imaged. Summary. So we have Barnard star has a good age. We're sure of that one. It only receives 2% of the light, and so it's cold. Could have, I didn't put any greenhouse gases in there, so it could be a little bit warmer than that. And the major thing with red dwarfs, this is pointing out a problem with red dwarf stars and habitability, is that when you want to be warm, you're going to get zapped. X-rays and ultraviolet, but if you want to avoid that, you're going to be cold, as in the case of Barnard stars. So I don't know if there's what difference that makes in terms of life. If it has water, if you don't know if it has water, you know nothing about these stars, about these planets. If it has water and it's in a zone where it's going to be frozen on the surface. And if it has geothermal radiation, it could be heated. It could have an ocean, could have lakes, or could have vents coming up where there would be ponds or little lakes where there could be water, liquid water, and therefore life. I use that quote from Jurassic Park, life could find a way. I'm not sure. And the other thing is that it is a candidate for imaging. Okay, thank you.
Okay, thank you all very much. Okay, we're going to go to the Q&A period. If you're on the webcast, please queue up your questions via the text chat, and Carrie will relay them to us. We'll start with questions in the room. I forgot to identify a mic handler. I need a volunteer mic handler. Can I get it? Where are my PIOs? Oh, okay, you're willing to do it? Great. Thanks, Mareki. All right, so wait for Mareki to bring you the mic and identify yourself and your affiliation and ask your question. All right, questions. We'll start with Ethan.
Hi, I'm Ethan Siegel, writer for Starts with a Bang at Forbes, and this question is for Edward. I would like to know, would this super Earth around Barnard B, would it need to be rocky with a thin atmosphere for life, or could it have a gas giant envelope? Like, could it have a large gaseous envelope and still support life? And if that part is necessary, right, if you need it to be rocky with a thin atmosphere, does that face difficulties given the Chen and Kipping results?
It's hard to know. If you're going to have the thermal heating and the oceans, it would be like Europa without an atmosphere, and there could be life inside. What I didn't point out is that during the pre-main sequence phase of the red dwarf, it was in the Hubble zone. It was warm and had liquid water briefly. So if it comes a mini Neptune, I don't know. I mean, I think it would be hard to have life on such a planet. So the answer to that is, if it's a mini Neptune, I would say the chances of life are small. It would be like like Jupiter, like Uranus and Neptune. Their moons have possible life, but I think the chances really go fastly down. Okay.
Hi, I'm Alan Boyle, just with a quick follow-up to what Ethan was asking for Edward.
Yeah.
What sort of information could you glean from direct imaging or other types of observations to resolve the sorts of questions?
It would resolve the question. If you see it and it's bright, you could tell the size and the reflectivity, albedo. You might even see rotation. And it's slow enough, the orbit is slow enough, 233 days, that you could image it for hours and it wouldn't move, unlike the shorter ones. Yeah, you could you could go to extremes and see rotation and do spectroscopy in the future, and you would resolve the problem. If you see it, if these people who did ask for time with sphere, if they see it, it is probably not good in terms of life. That would mean it would be a large planet in a dwarf, what they call dwarf gas giant, or a mini Neptune. And I think the chances go way down for life in those kind of planets.
Any other sorts of observations?
You can do, again, it's done by radial velocity. You know nothing. It's interesting when you do these papers, you're speculating. Because all we know about this planet is its minimum mass, how much radiation it's getting, its orbit, and that's it. And it's not a lot to go on, so you have a lot of room to speculate. It's a super Earth. We don't know much about super Earths. I was reading papers to try to find out, and they're all over the place. And in terms of what their structures are, if it has, it should have more. How much iron does it have? An iron core? Don't know. So you're speculating a lot here, but imaging would tell you right away. Seeing or not seeing it, how bright it was, and stuff like that, you would actually be able to know if it was a rocky planet covered with ice. Yeah.
Before we go to another question, I think Thane wanted to add something.
Yeah, and just to reiterate, this type of planet should be within striking distance for extreme AO systems on the 30-meter telescope, ELT, and GMT. With spectroscopy in the near-infrared, we could perhaps identify signatures of water. If somehow it had a signature of oxygen, we could perhaps identify this through the 1.27 micron line. If it happens to be abnormally warm, which it probably isn't, but if it happened to be abnormally warm, this might also be imageable in the thermal infrared at about 10 microns.
Since the sphere team at ESO is going to have a look, are you going to try to have a look with your system?
We may. I don't think I've seen a proposal coming in our system to look at it yet, but
There you go, Ed.
I heard, I was told there was a proposal. Maybe they were putting me off.
Okay.
Steve Mayer, freelance also for Dr. Guinan. Does your argument for possible subsurface lakes or whatever in Barnard B also apply to Proxima B?
No. Proxima B is in the temperate zone. It was blasted early on.
Why not under?
Well, okay, underneath, I guess it could migrate underneath. Proxima B was exposed to large amounts of radiation, which maybe got rid of the water. I have worries. I also do Proxima B, and I love that planet, but and it's in the habitable zone. At least you're warm there. But it had tens of thousands of times more X-rays than what the Earth was exposed to when it was young. And maybe it survived, You need a large magnetic field, first of all, and then if there's water there, or it could have lost all of its water and then brought in by comets and collisions. So there's always a chance of life in that manner. Yeah.
The less
You
we
go
know for sure,
underground.
the more we can speculate, right?
Yeah.
Okay, any question back here? Christine? Are there any questions on this side?
Christine Pulliam from Space Telescope Science Institute. My question is for Kate. I was wondering if there are any alternative explanations besides protoplanet collisions for the repeated infrared brightening that also could fit the data.
Because we really have a long time monitoring, we have a fascinating data. There might be some other speculations, say like a molten planet that just formed through a big collision could have volcanic activity, super volcanic that spew out a lot of dust. But this up and down pattern is semi-periodic. So you have to have a very super volcanic to create dump a lot of dust, eruption, and shut out, down a lot of dust. So you have to have this repeatedly for many, many years. And I think it's kind of hard, but it's possible if you have that kind of cycle. There might be some wires, other thing. We can rule out definitely it's not coming from the planet itself because the surface area is just too small. It cannot be the planet itself. It has to be some kind of dust, extended big thing, cometary cloud or dust cloud, dust from the volcanic eruption. Those are the most possible scenario.
Any other questions in the room? Do we have any online? Okay, we'll go online.
All right, we have a question for Ben from Megan Bartels at space.com. She asks, could you talk a bit about this work in the context of the search for extragalactic exoplanets?
Yeah, sure. Maybe. There's been several searches for extragalactic planets with HST. And I'm sure there will be more in the future with these large telescopes coming online in the next few years. And I think very similar methods will be able to be employed for those. The biggest problem or challenge with this technique is it's much more computationally intensive than it is to just draw a little box and count how many photons are in that box. And so we've been developing new ways to make that much faster using things like TensorFlow created by Google. And those have really made it more computationally tractable. And so I think in the James Webb, ultimately 30-meter telescope era, when we can get better angular resolution and separate these stars out slightly better, I think there'll be a lot of opportunity.
Hello? Okay, cool. This question is for Kate, also from Megan Bartels at space.com. How common are these sorts of observations, and how clear a picture do you think we'll be able to put together of how these impacts work?
How common are they? To see an impact, you really need to have observation through time. You have to have patience to watch it, right? The observation that I took is using Spitzer. And the early time Spitzer, they won't allow you to do time series observation. So we actually discovered this very late. And we just, after the Spitzer run out of cryogen, we start doing a more systematic search. And we monitor roughly a dozen of this kind of system. We notice a lot of dust, and we want to see whether we can see it. And maybe half of them show this kind of signature. And IDA is the most spectacular one because it has a long period of that we can monitor and get a very good data. So, half of the system that we think that should happen, this big impact, is there. The question is whether we can get enough data to actually monitoring.
Anything else? Okay.
This question is from Larry Marshall Freelance for Ed. The period of Barnard B is on the long side for planets discovered so far. Are there other similar objects in your sample?
No. Kepler has trouble with planets of that length because they're 90-day cycles. And it's a very tiny It's a tiny variation. It only has the radial velocity variation is 1.5 meters per second. It moves like this fast. And if it eclipsed, you could see it. It would be about 0.5% to 1%. So if with Kepler or TESS or things like that, they could actually see a transit. They would be able to observe that. But the 200 days is, this is 20 years of data it took to pull out something like that. And the signal is very, it's very hard to extract. Lots of they divided the team up into 2 groups to analyze the data separately and see if they got the same answer, same result. I don't know of anything that long as an Earth-sized planet. Of course, there's planets that have periods that long, of course. I don't know of any Earth-sized things.
Anything else? Any more questions here in the room? I have a couple of questions for Thane and Olivier. When you were describing the instrumentation and the kinds of observations you make, you're talking about spectroscopy. Are you doing actual spectroscopy with adaptive optics, or are you doing like imaging at different filters and getting a pseudo spectrum that way?
We use what's called an integral field spectrograph, which means that for every pixel in the image, we actually do get a spectra simultaneously. So it's a very efficient way to do spectroscopy because you don't need to separate finding the planet and taking a spectra. So the spectroscopy is part of the identification process itself of the planet, because speckles, essentially residual starlight, does not behave in color the same way as the planets themselves. That only goes so far in terms of the spectra we can get. So we also are working, and Thane showed there's another spectrograph that's much higher resolution, and we have an upgrade coming where we can put an optical fiber on the planet once we know where it is, feed that light to the spectrograph, and then get a much higher quality spectrum.
And I mean, we can also exploit this capability when we initially find a candidate planet to be able to tell whether or not it's worth following up. So the direct imaging field is challenged a lot by finding background objects, objects that are really faint, roughly comparable to the brightness we expect a planet to be, but are actually stars located at further distances. By having a spectrum, we can get an instantaneous measurement of its brightness at different wavelengths, so we can tell whether or not it looks like we would expect a planet spectrum to be, or a background star. Very powerful.
And will the TESS mission produce planet candidates that will be good targets for your equipment, or are they going to be too close?
Most of them are going to be too close.
This has been happening all day. They are having internet problems out there. I'm not sure what's going on. As always, feel free to ask all the questions you want in the chat. I will do everything I can to
But there may be some lucky overlap. We may have some test targets that are sufficiently wide to transit as well. And this would be fantastic because the data set we would get, the combined ability to have transit, hopefully radial velocity, so fully constrain the orbit and the mass of the planet, and spectroscopy from direct imaging would be fantastic. So I think we should be, hopefully we'll get lucky and be able to have that data set.
Yeah,
Go ahead, sorry.
yeah, and I think there's like an even stronger link between the Gaia mission and direct imaging, and also precision radial velocity, at least in the future, in direct imaging. So with Gaia, we can identify stars that show some evidence for acceleration that are due to hidden planets, and some of these might be around stars that are young, that have that are young enough where the planets could be imageable. And then in the future with TMT, we would then be able to target older stars and older planets and reflected right around older stars that have been identified through precision radial velocity.
Okay, any last questions here? If not, we'll wrap it up. It's 11:15. Let's thank our speakers again for their very interesting presentations.
Thank you.
A couple of quick announcements for the press corps.
That's how to phone.
I've posted direct
Okay, I'm going to close this down because you guys do not need directions to the press dinner. Thank you all for joining us here at CosmoQuest X on Twitch for our live coverage of this press conference coming to us from Seattle, Washington, and the 233rd meeting of the American Astronomical Society. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. We are a production of the Planetary Science Institute working in collaboration with Youngstown State University. Speaking of Youngstown, we are going to have Youngstown's own Annie Wilson, our own Binary Ablaze, joining us at 5 p.m. Eastern, 2 p.m. Pacific, 10 p.m. London time to give us an update of everything that's going on there on the ground at AAS where she is in attendance. Following that, we will go straight to live coverage of the final press conference of this meeting. We are here to bring you all the science we can, and give us a follow so you can find out when we go live with launches, landings, and everything in between. We will be back tomorrow as well to bring you the daily space at 1 p.m. Eastern, 10 a.m. Pacific. This will be our roundup of all that is new in space and astronomy. Thank you so much for the bits, Trekker Kev. We are sustained by you. Your subscriptions and every bit really matters. And the reason that we're here right now is because of your donations. We lost our NASA funding, and with the current government shutdown, we can't even try and get new government funding. So we're here and not shut down because your donations let us be here. Thank you. Thank you. That's all I've got. So if you have any final questions, go ahead and stick them in the chat, and I will answer everything I can. Sorry, I have screens in all directions, which I guess is the norm for a streamer. Okay. Thank you, Larry. It is a community, a collaboration. And don't forget, you guys can all join our Discord, which is where we hang out. And we are here, not 24/7. We do occasionally sleep and run to the grocery store and things like that. But we're here for you. So don't be afraid to reach out and ask a question or figure out how to get involved. So I'm not seeing any questions at the moment. So I'm going to say, I'm going to go get some lunch and some more coffee, and I will see you in a few hours here on CosmoQuest X. I'm going to roll the credits, look for someone to raid, and see you all, well, on the other side. Have a fabulous morning, evening, or afternoon, wherever in the world you may be.